This is a very short but an extremely important section. When we have covalent bonding, we have shared electrons between two atoms. And what we're going to talk about now is the theory behind it. And really, we can call that orbital overlap. So when we taught you VSEPR, that definitely gave us the shape. You began with the Lewis structure. You learned about VSEPR and how to count electron domains, but what is the theory behind bonding? How do these nuclei, the different atom nuclei, how do they interact in a bond? Well, we're Gen Chem, and we're not going to go much further than the simplest case of a hydrogen molecule. We have two electrons that are shared by the two atoms, and it's an overlap of the 1s electrons. There'll be a picture on the next page. I'm going to talk about it. But if we were to use words, we would say, well, there's an attraction for each electron by both the nuclei, and there's a repulsion between the electrons and between the nuclei. So when we are going to look at this, we're going to show how repulsion becomes more important. You're going to see a graph that maybe you've never seen before. So here we have it. In the earlier chapter, we said a bond energy for a hydrogen-hydrogen bond is 436 kilojoules. In chapter 7, we said that the bond length of hydrogen-hydrogen was 0.74 angstroms. So what you have below is a pictorial, all right? Here on the x-axis is the distance. We're talking about the distance between the two hydrogen nuclei. On the y-axis, we have plotted energy. And you'll see first the general shape of this curve. You'll see also a number here arbitrarily called a 0. I should mention that also. So if you follow this red line, what you see is it dips down and then it goes back up. So as it goes down, what it is the attractive forces are becoming stronger. When it starts to go back up, what we start to see are repulsive forces. So here's repulsive and here are attractive. So if I'm going to say what did those numbers mean that we had in the other chapter? Well, if I bring this line down to the x-axis, I will see that I'll call this an energy well. The distance on the x-axis corresponds to the bond length. It corresponds to 0.74 angstroms. If I now go over to the y-axis from this energy well, we will see it corresponds to a negative 436. And that's essentially what we chose as the bond strength when we were in an earlier chapter. So if I have a molecule as simple as H2, this is fine. If I have a molecule like HCl, also fine. Cl2, we're starting to push our limits. So it's very easy. All of these molecules are linear. But what about it says here, if I have methane? What's really happening in that? So what kind of question can you expect on an exam? I have to say that out loud. You may see a line drawn that looks like this. And what is that line saying? Well, it's saying a different bond distance and a different bond energy. Keep that in mind when you approach different problems. So, two hydrogen atoms, they can interact and they form the hydrogen molecule, which describes the stage of bond formation where the attractive and repulsive forces balance. I'm not going to read the words. I'm going to let you read the words. But I know that what they're describing is this general picture. And if the attractive and repulsives balance each other, it's going to be in that energy well. Realize it could be a lot of other things. We could have something that's drawn like this, saying the distance is smaller, implying maybe a double or a triple bond. I'll leave that to your imagination.